Hello and happy Friday, everyone. This is episode 98 of Get Your Tech On. I'm your host, Brady Volpe, founder of the VolpeFirm and Chief Product Officer at OpenVault, and I'm joined by John Downey, DOCSIS Senior Industry Consultant. Together, we're a duo of DOCSIS enthusiasts, which is just a nice way of saying we're two guys who can't get enough of talking about cable technology. So buckle up and get ready for a fun and informative ride as John and I contain our excitement about upgrading your HFC plan to future-proof it for the next 5 years. So try not to fall asleep, and welcome back, John.
Hey, glad to be back.
Glad to see you, John.
Notice all my hair?
Dude, I am just so jealous of that head of hair that you have. I can't tell you. Really annoys me, man. You're getting younger and younger by the episode. How are you doing it, man?
So I was tired. Now I'm retired.
Retired. I could go on it.
I turned 57 on Wednesday, so 2 days ago.
Happy belated birthday to you.
Thank you. And about a month, maybe 2 months ago, I said, you know what? I'm going to grow my hair out just to prove I can. I have no idea where my hairline is, so let me grow it out and see what it looks like.
Yeah, I'm going to try that too. I'm going to try to grow my hair out and just see if I can.
My wife's like, just tell her when you pull it from your back.
It's pretty impressive. I'm sure there's a lot of other people out there that wish they could do the same. So, John, as we lead into our discussion of upgrading HFC networks, and we'll talk about why we're not discussing fiber to the home in just a minute, I have a couple of news pieces that I think are going to be important to our readers. According to Fierce Network, ATX surveyed 150 cable professionals for its annual 2050 project survey. 70% of respondents plan to turn up DOCSIS 4.0 by the end of 2026. Full duplex DOCSIS 4.0 is emerging as the more attractive deployment option. And according to Jay Lee, Chief Technology and Strategy Officer at ATX, from an FDD perspective, the underlying equipment is or will be deployed supporting bandwidths up to 1.8 gigahertz. So if you want to call that 4.0, yes, you certainly can. Again, that was according to Jay Lee from ATX. So those are some interesting responses, John, that 70% of operators are strong on DOCSIS 4.0, which means that they're likely to expect to get a 5-year return on investment from their purchases. FDX is emerging as a more attractive deployment option than FDD DOCSIS. That's super intriguing. And it looks like 1.8 gigahertz downstream is a foregone conclusion, not a nice to have or a pipe dream. Some really interesting things. I'd be interested in your thoughts on that.
I think the 1.8, like you always want to keep talking about, let's just upgrade our plant one more time, be done with it. And that's where the analysis paralysis always comes in. You're like, all right, do I do this? Do I do that? Do I just heck with it? Just clean it all out, just wipe it away and do fiber, But we're not going to do that because we keep, using the coax we have. We know that we keep getting new technology with higher outputs, better technology, lower power draw. And if we can keep using the coax that's there and not have to respace amplifiers, because that was a big problem, right? If we go to 1.8 gigahertz, there's so much loss in coax, we might have to respace the amplifiers just to make the end-to-end levels. But we're able to figure out how to have higher outputs, higher frequency. That's the higher outputs are for the higher frequency, and not have to respace. Right. So that was kind of a kicker right there, is how do we do that? So new technology is allowing us to do some of this. So why not go to 1.8 and be done with it? The FDX ESD conundrum really is the upstream and the diplex filter.
Yes.
Do I get rid of the diplex filter? How do I get rid of the diplex filter? Do I put a diplex filter that's controllable so I can control it and make it an 85 split? And then down the road, I make it a 204, 254 split. And down the road from that, I make a 396, 500 megahertz split. Or do I not do a diplex filter at all, which is FDX, and I have to add in circuitry called echo cancellation?
Yep.
So, and maybe I have amplifiers that will do that, and they'll have a plug-in device. I don't know. Or maybe the diplex filter is a plug-in device, so you can swap it out later. The bad part about that is truck rolls. But it's better than having to rip out a housing or rip out an amplifier module, right?
Yep.
So if I can put something on the pole, and later down the road, we all know our RF expertise and technicians, they're falling away.
It's not getting stronger over time.
Yeah. So down the road, we might have we need more plug and play,
Yes.
right? And plug and play, whatever you want to call it. It's like you're going to have someone that doesn't have that RF background 3 years down the road. It might have to just swap some stuff out. And usually MSOs are hiring subcontractors and stuff like that. So they're doing piecemeal as fast as they can, go down the line and be done. And we want it to be fast also because we can't have interruption to the end customers.
We can't take them down. We can't take them offline.
Yeah. And we can't do it in the middle of the night because people are working in the middle of the night too.
Yep.
You know, what is off time? There is no off time anymore.
So Charlie Moz asks us a great question in chat room. He says, would you guys opt to upgrade a plant from 6585 to 204, 258 megahertz, or skip the CAA spectrum deployment and go with DAA? If the latter, why? So Charlie, we're going to be answering that question for you in today's episode. That's part of what we're talking about today, so don't leave. John, I want to talk about one of the elephants in the room. Is why even bother with this conversation? I get comments all the time on the YouTube channel about why are we wasting our time with DOCSIS? Guys, just go fiber to the home, people say all the time. I mean, come on, John, this should be a no-brainer, right? Give me more fiber in my diet already.
I think people, they got enough cleansing with their fiber. Everyone's tried it. People have tried it. It's money. It comes down to money.
Indeed.
It comes down to right of ways. It comes to, and it might not be, fiber through the neighborhood is fine, but we used to say the last mile. Now it's the last 100 meters. How do I get from the pole into the house? I have to sync up with a customer. I have to deal with dog fences. I have to deal with dogs. I have to deal with underground. I have to deal with the ONT. Who's going to power up the ONT? Well, it's got to be the customer has to power up the ONT. Coax is already there. Why mess with it? If it ain't broke, why fix it? So, just leave it alone and lose it. So that last bit could be the hard part to deal with, the hard pill to swallow. So I always said fiber to the tap is even better, because you're getting really, really close. But, to have to replace into people's yards, that's a little bit more difficult.
And I think, to your point, many people don't realize that we already have fiber going very, very close to the home. The packets of data spend like 99% of their time on fiber. And then they go to the fiber node. That fiber node, most of the time, is in people's neighborhoods. We convert that fiber to electrons, and then those electrons are distributed over coaxial cable. That, to your point, that last mile, that last little bit, because that is the most expensive, the most difficult part to run fiber from where we have fiber nodes to subscribers' homes, particularly because of right of way, because of costs, getting permits. And then when you start plowing through people's yards, it gets extraordinarily expensive. So it is a big challenge. If cable operators could do it and not go out of business doing it, it would definitely be more cost. Maintenance would be easier. So many things would be easier. We could run higher speeds much easier. But the fact is, it's not. It is very costly and very challenging. Over time, cable operators are slowly moving in that direction. But when we look at the numbers, DOCSIS is the more cost-effective way to go, and we can do it today. To do fiber everywhere is going to take time and a lot of money.
I think a lot of people ask the question might be myopic, meaning they see their situation, and they might live in a neighborhood that has a house. I'll give a case in point. I live 700 feet off the road, right there. On my 1 mile road, there might be 10 houses.
Yes.
So, you're probably still going to have an N+3, N+4 architecture, because you're not going to run a fiber to hit 2 people and a DAA node to hit 2 people. You're going to hit the DAA node somewhere down the road, and then you have to run coax, but we're so far apart, one amplifier is not going to be enough. So you're going to throw another amplifier, and it's already there. The amplifier's already there. It comes down to the money, bean counters.
A recent convention that I attended, they talked about density, and it's easy to push fiber where you, exactly as you said, you have dense housing, dense markets. That is cost effective. But as soon as you get into like rural areas, homes like you're talking about,
Yeah.
that makes it very unattractive, and the numbers don't work out. I was also surprised to find out when you talk about the fiber, how far AT&T and Verizon have pushed their fiber deployments. Both companies are under 20% deployment, like homes passed in North America. That was very surprising to me, because if you look at Coax, we're well in the better than 90% home passed. So fiber is very, very sparse versus Coax is very, very dense. We have very good coverage. So that's I think that's why we are not talking a lot about fiber right now, and we're focusing on Coax and DOCSIS. So today's topic is crucial for cable operators looking at upgrading their hybrid fiber HFC. So there is a lot of fiber in Coax. That's why we call it hybrid fiber coaxial plants. We have to meet the growing demands and stay competitive. So John, I think you can really be the person that can start explaining why and how some of these upgrades should occur to HFC plants, and maybe what some of those challenges are.
I used to start writing HFC with a small c.
Yes, the C is small.
Fiber, small coax.
99% of fiber.
We're getting the coax down as much as we can. And people are going to deploy fiber where it makes sense, economic sense, right? Ease of access and all that stuff. You and I talked about what are our other options. The bottom line is people want speed. Right. They need speed. They want speed. They want lower latency. We just have a lot more stuff that we're getting over the top, over the internet. So it's like, how do I provide more speed and better quality of service and all that, or quality of experience? You and I talked about satellite. I had satellite. People complained a lot about my satellite connection.
They can look back to some of our older YouTube videos we did like years ago when you were on satellite, and you would be like this when you talked. And that's why we didn't get so many subscribers. So today your video is much better. So please like and subscribe and hit the notification bell for John's great video and voice that we have on this video.
Started with HughesNet, and it was painful. It's a geosynchronous satellite, so it's 22,000 blah 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 miles above the equator. So the latency there is going to be
terrible.
Milliseconds and not nanoseconds. It might be a second. But either way, I started doing my audio over the cell phone and my video over the satellite, and my voice would be like, you see my lips.
It was seconds behind, like 30 seconds behind.
Yeah, it was bad. So that was painful. Now I have fiber to the home, which is awesome, and I think anyone would take it if they could get it. The other options, like Elon Musk Starlink. I heard about $500 for a dish. That's hard for some people to swallow, especially people in the rural areas that might be older. That like, I don't need it that bad, And I think they charge about $100 a month, give or take, for. The speed's not bad because it's low Earth orbit, LEO. It's only like 300 and some miles above us,
right?
Or depending on where you live. It's not geosynchronous. It's not over equator, right? But you might see a whole line of these things going across the sky sometimes, like aliens. It turns out it's Elon Musk just shooting off another.
Making more money.
Yeah.
Then fixed wireless access, like 5G. There's a lot of people that are starting just to say, "Hey, I'm just going to cut everything and just go with an access point in my home."
Yeah, the 5G had a lot of fanfare. You would just throw 5G out there, and people are like, "Oh yeah, the next best thing." You know what I liken that to right now is AI. People are throwing around AI wording like they threw around 5G 3 or 4 years ago. It's just the next best thing. No one really knows what it does. And it's definitely not just an Excel spreadsheet. Yeah, I'm doing AI. No, you're just crunching numbers. Artificial intelligence is all right. So we have options. I told you that, the actors from Scrubs, they did their own commercials, like John Cena or The Rock is on there also, talking about no wires, doing like a musical, and they're pumping up Verizon's 5G hotspot. And I'm like, that might be fine if you live in a city where you have good connectivity, but the more people jump on it, it gets clogged down too. Everything's shared at some point. And I used to think wireless would be good too, but I think you're always going to want a wired connection, at least one.
I've definitely heard success stories, though, from people who are very satisfied with their 5G access points. They've cut the cords all together, and they're saying they've got great service with it. So I think it probably depends on where you're at, the use case, what type of services you're running on them. So for
How
some
many in your
people,
house?
FWA, fixed wireless access, is a good solution.
Yeah. You might even say a lot of empty nesters will be fine with it, right?
Hmm.
But when you got
Absolutely.
kids and you're doing 5, 6, 7, 10 devices in your house all doing stuff, yeah, it'll bog down after a while, or you'll be fighting for capacity. Or
But as we look at newer services, so like the Google Vision Pro or the Google goggles, I
yeah,
I believe those run something like hundreds of megabits per second on the amount of traffic that they draw. So that newer technologies can and will likely be problematic for FWA, fixed wireless access. And that's something where now, to your point, you're going to want a hardwired connection, whether it's DOCSIS or fiber, for
yeah,
newer service. So again, it depends on the use case, I think. And I think that brings us back into the DOCSIS space, and maybe even back to Charlie Maz's question of, am I good with a 42 megahertz return, or am I going to want to expand my plant to be, to make it solid for the next 5 years? So,
yeah. I think a lot of people in the U.S. we were 42 megahertz. Jumping to 85, you doubled the spectrum. So that was a good investment, jumping to 85
yep,
megahertz. And there wasn't a lot of stuff between 42 and 85 that we couldn't get around. Some analog channels that we decommissioned. We went digital anyway, because you had to get rid of channel 2, 3, 4 on your downstream system if you went to 85 megahertz. It's 55.25, 61.25, 67, right? So we had to get rid of those downstream channels, which a lot of times we already did that. Most people already did that. So an 85 split was perfect. If you're 65 megahertz in the UK, you're not going to go to 85.
right. That's that
From
that
right,
that extra
that's
20
great.
megahertz isn't worth
Yeah,
it.
you might say, all right, I can do decent with 65. Let's jump to 204. That makes sense. I mean, that's almost 4x, right? 4 times the amount.
Correct.
So that makes a lot of sense. The 204 254 split, it's high enough up there to offer a 1 gig service on the upstream.
Which is
The
what,
aggregate,
two 96 megahertz OFDMA channels in that
yeah.
upstream.
And if you could do 1K QAM, because it's a decent clean and it's more robust, right, than single carrier QAM, you can get about a 1.6 or so aggregate speed. So you could offer a 1 gig service and be comfortable with it. And I think that was our panacea, right? Our holy grail, how to offer a 1 gig upstream service, especially if we're going to do a 1 gig by 1 gig, symmetrical service if we
Right.
needed it. But even just having a bigger aggregate allows me to sell more 500 meg services on the upstream, right? Or 100 meg services, a lot more. A bigger pipe means I can share it more. So 204, 254 offers good speed. The modems on the market support that split. It's not going so far up in spectrum that's eating more of my downstream. And when you go up in the upstream downstream split, the diplex filter gets wider and wider as you go higher up.
Mm-hmm.
So basically, the diplex filter, no man's land, is 20% of the highest, 20 to 25% of the highest upstream frequency you use. So
And that
take
no
20%.
man's land means that you're actually losing some capacity. You're
Yeah.
losing some usable spectrum that you have.
Yes. Yep. So if you went to a 396 upstream, I believe the split is a 396 500.
Yep.
That's 100 megahertz you lose because you just want to use common technology with diplex filters. So we got to come up with new technology.
Yeah, Charlie kind of, and there's a bunch of you on here, guys. So don't leave Charlie alone here in the chat room. But Charlie comments, he says, "I understand that the space power savings in the head end. So another thing we have to think about when going to 204 megahertz comes with DAA deployment and
Yes.
reduced cost to node split. But if 204 expansion gets you capacity you need, why go DAA, John? All the head end work is where the money's at."
So I would always say that DAA is inevitable. If you go 204, I remember CommScope came out with a solution, with the Air CommScope solution, I think, that they could do remember we had EDRs and BDRs, baseband digital reverse?
Yes.
You would digitize the upstream and send it back. They made something like that for 204, where they actually digitized it and send it back. So it was still an analog node, which was kind of cool because you could still do your CLI, your cumulative leakage index signals, my downstream set-top box signals, all that stuff, because it's still an analog node.
You preserve all your legacy test equipment that way too, then.
Yeah. I think we're past that point where we're like, you got to go DAA. And it's not just for the power savings in the head end. It's the RF connectivity. When you do more node splits also, you have more upstreams you have to connect in the head end. So you need more upstream receivers, more CMTS ports. If you go DAA, it's all optics in the head end. And all your ports are out in the field. They're already segmented.
Yep.
You know what I mean? They're already separated in the field. I don't have everything coming back to one place in the head end. But DAA allows me to not have upstream laser clipping because I'm not changing the intensity of the laser with the RF going into it.
Yes.
I'm doing a digital upstream. It's just on, off, on, off, on, off, right? So going digital fiber makes a lot of sense. Power, performance, no clipping. So it makes things a much cleaner.
It takes away so many analog optic problems. Yeah. And we had a good comment from Tom here. He says, hello, from a really small operator point of view. And Tom, you're not the only one. There's Tomas, I'm sorry. There's a lot of others out there. It was a great decision to go from CAA to DAA to 1 gigahertz and 85/105 and open patch to 204/256 and VCMTS, virtual CMTS. But decisions almost 5 years ago. So that's amazing that you guys were way ahead of the curve, Tomas. Congratulations to you. I'm sure that's paying off dividends now as you know, we're really talking about this for operators who've not made that jump now.
Yeah. Imagine if you were still an analog upstream laser and it might have worked for you even at 204 because you haven't used it yet. Meaning, once I have more capacity and people start using it all the way up to 204, that means there's more energy hitting your upstream laser. So that upstream laser, man, I had laser clipping when we went to 85 megahertz.
Right. People had laser clipping at 42 megahertz. It was a
so
problem.
I said, once you go to 204, DAA should be inevitable. I mean, that's what you should be doing, a digital upstream. But then they came out with that baseband digital reverse or enhanced digital reverse to digitize it. And I'm like, just got to bite the bullet and go DAA. I mean, you can go so much farther. And we found out that we could actually go much farther than what DOCSIS typically does. So we could go from a head end and collapse a hub site and go 1,000 kilometers away with DAA. We didn't, normal DOCSIS is what, 20 miles? There's a certain time that it's a
timing offset. It's the round trip time delay that you suffer from.
Yeah. But in reality, most people have the node maybe only 20 kilometers, 30, 40 kilometers away. So DOCSIS can deal with that distance, but when you start talking about 1,000 kilometers, in theory, you could collapse hub sites down or small head ends and do one major head end and then do DAA all the way out, 1,000 kilometers away. So that's kind of the nice thing. So we're not here to talk about DAA, right? I'm assuming we're already DAA.
Yeah.
But what do I do with my plant that happens to be out there? If I have my RF plant out there, I want to upgrade it one more time, maybe, and that's it, and be done with it or retire. I don't want to have to deal with it later. So
yeah, and it can't all be roses. I mean, this can't be something that's just easy for your operators to do and set it and forget it, right? There has to be some challenges here, John.
Yeah. So I see options on the taps and the passives. There are some new ones out to 2 gigahertz. I think the spec was 1.8 for extended spectrum DOCSIS 4.0, right? But if I can get the 2 gigahertz, why not do it, right?
Well, according to Jay Lee, it's like 1.8 is going to be, a lot of the equipment's just going to be designed for 1.8 gigahertz as well. So 1.2 is going to be relatively easy, maybe.
Yeah. So a lot of, I see some are promoting 2 gigahertz, which that's fine, whatever. If you can go past 1.8, fine. And it might be the seizure screws are a little bit different. We want to make it as easy as possible. So if you have to change out the tap housing, that's more work. So there might be heat shrink you got to cut back, disconnect the connectors, put new housing in, connect it back. If you ever have to cut connectors, you remember this. Remember when they came out with the 9-inch tap?
Yes.
Remember the stretch tap?
Yep.
They did it on purpose because if you ever had to cut the old tap out,
you're going to have less cable. So at least now you have that cable because it taps the amplifier housing bigger.
You have a bigger tap, so it would make up for the cable you cut off, and then you would connect it. So that made sense. So if I have to cut stuff off, that could be a non-starter, or it could create like small issues or whatever. Or you're doing little extenders on coax, which you don't want to be doing stuff like that, right? Anytime you have a connection, you have an impedance mismatch. I don't care how good you are at your craftsmanship, any connector you have is going to have an impedance mismatch. Yeah. It might be 72 versus 75 ohms. really tight, but it's going to have some slight nuance.
Yeah, even amplifiers themselves. I mean,
Oh,
as
yeah.
we both worked
Record
at
turn off.
C-Core, or I worked at C-Core, and you hung out there.
I was a boy.
When we designed the RF amplifiers, really the best return loss we could get out of them was about 18 dB return loss.
Yeah.
Some of them were only 16 dB return loss. And when we think about what's the best return loss we would want, it would be like 25 dB or higher.
Yeah.
So that means when you put an amplifier in, even if you did the perfect job of putting connectors on, the presence of that amplifier in there caused a micro reflection.
Yeah.
So
And that,
just because it's not perfect, it's not ideal.
I used to tell people another way to think about it, if that, call it reflection loss. It's the loss to reflective energy.
Right.
The return loss to reflective energy. I want as much loss as possible because I don't want any reflections. So I want that to be a high number to dissipate any reflection, right? So 20 dB return loss or reflective loss is great, 20 dB and higher. But that's also frequency dependent, right? There's usually a graph, and it might not be as good of return loss at certain frequencies, or maybe the ones you're not really worried about, it's actually worse, but you're not worried about them. Yeah. So yeah, you can say you have a certain return loss, but then it's also frequency dependent.
Now, the thing that an amplifier does have that a tap that you mentioned does not have is an amplifier has isolation in both the forward and the return. An amplifier in the forward also has something called an automatic gain control or automatic level control. So that over temperature, it keeps the signals at a constant level, because temperature changes causes plant levels to change over time, causes amplifier gain to change, causes attenuation in the plant to change. But it does not have that in the return. And as we talk about going to higher and higher frequencies in the return, we're going to see more and more loss that varies over temperature in the return. And I think that is going to be problematic, especially as we go to 204 megahertz, as we go to DOCSIS 4.0, it's going to be even more problematic. So how do cable operators deal with that, John? How do we deal with this higher loss in the return? And is it even something that we have to worry about?
Yeah, can I share the screen now?
Yeah, absolutely. You can share it anytime you want.
Let's see. Let's share the PowerPoint. And this was, let's go here. Can you see that okay?
Yes, we can.
All right, so this was this easy graph, and this was kind of extreme. This was a temperature chamber. Chris Leghorn was working with me. I was working with Chris Leghorn at C-Core, and this was in his Lawrenceville, the old SA facility in Georgia, on Sugarloaf. And he was running a 5 amp cascade. And it's extreme because it's 7,000 feet of half-inch coax. So that's extreme, right? 7,000 feet.
That's a long distance, yeah.
Yeah, so 5 amp cascade. But you're looking at different graphs of temperature and levels or loss for that amount of coax. If you look at the blue one, that's a plus to minus 5 dB swing in loss in coax at 85 megahertz.
Just at 85. Yeah, that's pretty significant.
We didn't go to 204. So you could have a 10 dB window there when it's super cold out and then when it's super hot out. And we talk about what does hot really mean. The rule of thumb used to be black jacketed aerial coax that's sun loaded could be 40 degrees above ambient temperature. That's 30 to 40 degrees. So when you run numbers, you might say, well, it might be 100 degrees, but it's really 130 or 140 on that coax.
You'll easily, coax will easily hit that temperature as it heats up, especially with solar loading. Buried coax, no, you're not going to hit that. But aerial coax under solar loading easily will hit that temperature. So
then you got, it's hotter temperature. It's funny. People used to say, is there more attenuation because the coax gets longer? I'm like, no.
It doesn't get that much longer, man.
It does get longer, and that's why we have expansion loops, right? That's why when it gets colder, that expansion loop will actually pull out a little bit. But that's not it. It's and I think Ron probably did an episode with you, didn't he?
Yeah, I think we did cover that on what the effects are that cause that.
Yeah. Like the electron movement, and that was affecting it. So if we could keep our coax cold, it actually would be better.
Yeah.
We could pump in like super collider, superconductor.
Minus 400 degrees Celsius.
No resistance. Yeah, it would be good for DC loop resistance, and it would be good for attenuation. But my point is the hotter it is, the more attenuation there is, the more the modems have to jack their levels up to hit the CMTS back to what it wants, which is usually 0.
Yep.
So now I have a problem with the modems maxing out in power. There are some gotchas or catches at the CMTS to say, hey, I'll let you stay online if you're within, say, 6 dB of my optimum. So the CMTS is like, I want 0. If you max out your transmit level and you're hitting me at -3, I'll let you stay online, but know that you're going to have a 3 dB worse MER than everybody else, right?
Yep. Stay online, but the performance could be impaired a little bit for the end user.
Correct. The nice thing about OFDMA is maybe it is affected, but the modem itself can drop to a lower modulation.
Yep.
So that's kind of nice. DOCSIS 3.0 and 2.0, you're stuck. You're at 64 QAM. If the MER is bad, it's probably going to just drop offline or hopefully go to partial mode.
Yep. Hey, in the chat, grab a sandwich. Glad you made it. I was afraid you weren't going to show up today. You said upgrades to last 5 years? Shareholders only care about the next quarter. Probably true, but we care about the next 5 years. Grab a sandwich. Glad to have you in the chat. Thomas says, about power and save the dollars, we reduced from 2018 head end from 20 kilowatts to 6 to 8 kilowatts. That's an amazing power reduction. That is awesome to hear. But in the field, power increased a kilowatt, more than 860 megahertz in the network. So there's a trade-off there. That's not bad, though. You saved from 20 to 6 to 8 kilowatts. So that's, I mean, like more than a 10 kilowatt reduction in the head end and only a kilowatt increase out in the plant. So I think that's an awesome story. So congratulations on that power saving story, Thomas.
And that's like the fuzzy math, and marketing guys will do that a lot. It's like, man, if you digitize your head end and you go DAA, we can get 5 racks down to 1 rack, and we get rid of all the video QAMs. That was a big one, the video QAMs. Get rid of all the video QAMs. You condense everything down. All it is fiber going out, and you save all this power. And not just the power, but the HVAC, BTUs.
Yeah.
Right? Because you have the
heating and cooling. It's mostly cooling, really. You don't need to heat.
Cooling. Yeah. You get rid of all that. But aren't you robbing Peter to pay Paul? You're taking that RF, that optic to RF transition out to the field.
But I think what we saw is really not that much. I mean, there is some powering that's going to occur out in the field, but it's
and the good thing was, because it's out in the field, maybe the nodes have better heat fins, heat sinks.
We don't have to AC the outside.
Yeah. And then you also had newer technology that was a little bit more friendly out there and more powerful and more RF output with less power draw. So there still wasn't there still a 50 watt? Was it 50 watt limit?
There is a limit on it. They've increased the limit with DAA and stuff. Yeah. I don't know what that limit is. I'd have to go back and read in the spec. So.
But it is right. You're putting more nodes out there, so you're requiring more power out in the field.
It is more power,
but it's still a huge savings when you do the math, right? It's still a huge savings.
Yep. So thanks for that, Tomas. That was good input.
So that's the DAA side,
so that's 84 megahertz. What if we go to 204 megahertz? How does this change now, John? Do we?
Yeah. So I mean, you could extrapolate those lines and be like, God, that could be like a +10, -10 swing. Yeah. If you really went out that far. I have another slide here that I tried to. I don't know if I can run slideshow from here. I guess it doesn't really matter. Yeah. But I was showing maybe a typical design where we used to say we want 17 input on the upstream to the first upstream amplifier. We used to have 26 dB taps, so I kept it in there. A lot of systems dropped to 23 dB taps because of upstream issues, not really downstream, but upstream issues. But I kept it in here just to show a kind of a worst case scenario. I have 350 feet of half-inch coax from one tap to another, 500 feet to another tap. I might have a field equalizer, an inline EQ. That's a hardline passive. And then my last tap is a 4 dB tap. Now, we know our taps are selected based on downstream requirements. That's how we select our tap values. And then upstream just has to work. So when
make it work in the upstream based on whatever the downstream is, which the upstream's kind of important for us.
Yeah, now it's even more important. But I was just showing if a modem was right at this tap, I'm not even talking about drop line, right? It's right at the tap. I'd have to transmit 43 dBmV off the first tap. And ironically enough, the modem that's farther away transmits less, right? Because it's a lower value tap. And at that low frequency, let's say 30 megahertz, there's not much loss in the coax.
Right.
So the tap values were selected on downstream, and the coax loss on downstream frequencies is a lot, but on the upstream frequencies isn't. So this coax nonlinear loss is an issue for us.
Yeah. And just to quickly remind everyone, that modem off of that 4-value tap transmitting at 38 dBmV.
Well, actually, 29. It was 29.
Oh, it was? Okay, I'm sorry. Transmitting at 29 dBmV, that's a bad thing, right? Because if the modem is transmitting at a low power, then it's only going to be transmitting a little bit out of the noise floor. That will cause low MER or low SNR. We want that modem to transmit higher.
Let's clarify that, because people are confused by that. They're like, if a modem transmit lower, will it have a worse MER than everybody else?
Depends.
Let's look at the big picture. It's not, because it's still going to hit the CMTS at 0.
Right.
And it still has the same noise floor as everybody else.
Correct.
So making it transmit hotter, what does that really do? So it's not that it's making that modem better. I'm going to induce loss on purpose at the tap to help drop the noise from that house.
Correct.
So
because you're not putting the attenuation at the modem. That's the important part.
Correct. I'm trying to add attenuation where I think ingress will get in. And it's usually the lower value taps from the house through the ground block up to the tap itself.
Right.
So I need something at the tap to force the modem to go hotter, and not just to go hotter, but to drop the noise also from that house.
If only we had a device that could do that.
So they came out with step attenuators. They came out with reverse upstream padding for the field equalizer. And then they said, instead of putting these pencil pads on all the spigots of a tap, can I just make a tap with some attenuation built into the tap? So why not just do a flexible solution tap or a conditioned tap? So then they started making sort of like a step attenuator in a tap. But I would say, I don't want to do that either. Because if it's a split, a 42 megahertz upstream pad, that's a diplex filter practically.
Yeah.
That's a group delay. And then what happens when I go to 85 megahertz or 204 megahertz? Now I got to change all those devices out. I want a tap that's equalized from 5 megahertz up to 1.8 or 2 gigahertz.
And we really need that when we start to talk about, things like full duplex DOCSIS or changing from 85 split to 204 to 396 split. When our future split is uncertain, and we don't want to have to go out and replace all these equalizers that we put in. Charlie Maws made the comment, equalizable taps should be easier to deploy, cheaper, much easier to balance coax runs with wide spectrum. So I think exactly to your point, John.
And it's not just the end of line, right? It's also the first tap. Remember, what's coming out of your amplifier in the downstream is a highly, highly tilted downstream signal. So do I really need that much power and tilt going to my TV or my set-top box? So the only place it's probably flat is in the middle somewhere, because it comes out tilted, positive tilted, and as it goes to the coax, the downstream's level is negative tilted. So equalizer, end-of-line taps would flatten it out. Cable simulator, the first few taps would flatten it out going to the TV sets or the set-top boxes.
So how do smart amplifiers help with this problem, John? Amplifiers that have pads and equalizers in them that automatically adjust to that. Is that a solution to this? Will that make all this problem go away for us?
No. The smart amplifiers were really there because we're losing RF technician expertise. And we're trying to do plug and play, plug and pray.
Yep.
And we want to be able to put in new amplifiers for the next generation, but not have to go through sweeping and balancing and then the human error that comes with it.
Yep.
So I want a smart amplifier that can, I don't have to carry around a tackle box full of all these pads and equalizers, right? And then I had upstream and downstream equalizers, and the pads were in 1 dB increments or whatever. And I had a whole tackle box I had to carry around, and then you had to give it to all your technicians. Now you're like, you know what? I can get rid of all that, and I can have an amplifier that just does it with electronics.
And I think that's important for people to understand. Smart amplifiers doesn't mean we're getting smart taps yet. We still have these same problems.
Exactly.
We need a smart tap for Charlie so he doesn't have to worry about these problems.
Yeah.
Grab a Sandwich says,
right.
Yeah, Grab a Sandwich says fiber to the home probably saves a bunch of power. Do you think MSOs will ditch HFC in the near future to compete? Many customers eligible to HFC are increasingly showing a negative attitude towards cable. Grab a Sandwich. I think you did miss the beginning of the show because we covered
Yeah.
fiber to the home and the cost. AT&T and Verizon are covering less than 20% of the market. It's really expensive. You have to go back. Rewind, Charlie. We got that at the beginning. Modems transmit varying based on distance to HVT versus LVT. That just shouldn't be a problem. We should rightly have the ability to balance the loss at taps near amps to provide the same transmit power as modems furthest from the amps. A true unity transmit networks.
Yes. If we really did take the time to have every modem on the plant transmit, I used to say 49 dBmV, maybe 48.
Perfect.
48
That would
dBmV.
just be perfect.
Because then I have about 3 dB of headroom to 51, where the max was for DOCSIS 3.0 and 4-channel upstream bonding. Then they came out with an extended power 3.0 modem. So if you went to 8 upstream bonding, now we're doing OFDMA that's 65 dBmV total power, and you got to do the math of what that really means. But if you had it set up that no matter where you were in the plant, which tap you were, that you were transmitting close to 48, I think you were safe, and you designed the plant with a proper attenuation to drop the noise floor for everybody. And that was the key, trying to get the best quality of service and the best noise floor for everybody.
Yep. So Armin says he's not familiar with these smart amplifiers. Are these common for some providers? So Armin, there's actually a spec that Cable Labs has put out on smart amplifiers. So if you want to get into the really nitty-gritty details of that, check out cablelabs.com. Look at their specifications, Google, or search on smart amplifiers. But John, I will let you, because I think you're doing some consulting with a company that works on smart amplifiers. I'll let you address what exactly smart amplifiers are.
So I took early retirement from Cisco in October, and then I got convinced to do some contracting for Technetics they're out of Europe and Netherlands and UK. And I liked what they were doing with the RF side, which I thought, RF was kind of dying off, but they were doing a lot of cool stuff with powering, with RF amplifiers, a diplexer-less amplifier, which was kind of cool. It was set up with just enough gain in upstream and downstream and isolation that a diplex filter wasn't needed. I'm like, well, that's cool because
Super cool.
I don't want to put all my eggs in one basket, or I don't want to hedge my bets, right, on what split is going to be needed. If I could put something in the plant that doesn't matter, I could do FDX, maybe. I could do any ESD split I wanted to, 396, 85, 204, 495, 6. It doesn't go to 684. DOCSIS 4.0 spec goes to 684 in the upstream. So that's one of the options.
That's a big upstream.
Yeah,
684 megahertz in your return. Imagine that.
Yeah. And then going that far up, then you eat into your downstream that much. Now you got to make sure you go to 1.8 on the downstream because you ate so much of your downstream from the upstream. So all these things come into play. So where were we going with this?
What's a smart amp, John? What's a smart amp?
I digress. I digest.
EQs, pads, all smart.
Yeah.
Maybe even an ALC in the upstream.
Yeah, and that's the big one. I think when I ran numbers for 204, I think there's enough headroom in the modems to make up for temperature swings and 204 megahertz upstream and coax. On the downstream, we had automatic level control, so if the levels changed a little bit, the modem or the amplifiers had a little bit of reserve left in them to change the level to keep it steady. On the upstream, we didn't give a crap because it was 42 megahertz. How much real swing could we have at 42 megahertz? Like nothing. 85, nothing to really worry about.
John, Armin's saying stay on target. How do you remotely adjust the pads and EQs, or do you need to plug pads and EQs in these smart amps, John?
Oh,
focus,
so that's
man.
Where we started, wasn't it? The smart amps. You're the one that threw me on ALC. So it's all electronic, so it can control the bias current to the hybrids. It can control the levels. The pad itself is an electronic pad that's in there that could have a out of band or in band status monitoring. So it could be an app that you plug in. It could. We're not going to do Bluetooth because it's probably going to be worried about security.
Insecure.
Yeah. So you plug in, and the technician could set it with an app on their phone, or if it's all set up for out of band or what I call in-band status monitoring, I could be at my head end or home even and say, all right, just make sure this guy is actually set up for the proper levels. And the pad and EQ can adjust through electronics to get the right levels. So once it's set, the background communications can just make sure it's staying where it needs to stay. To take that a step further, we can do power savings because we can bias the current. You might say, I'm only going to 1.2 gigahertz right now. I don't need gain out of this hybrid to 1.8 because I didn't even activate anything. Let me just shut it off. So I could shut down power to the hybrid for 1.2 to 1.8 and save power for maybe 3-4 years. Right? So I want to deploy something that's future-proofed, but I don't want to have to pay for it all those years. So I could have smart amplifier that can bias the current. You know how we were talking also about if we go to 1.8, people were talking about doing a stair step. It's like
instead of having a constant tilt output, they'll have a tilt, drop down, and then as you go higher in frequency, it'll just continue stepping in order to manage the gain of that amplifier.
Yeah, you can have a tilt, drop down at 1 or 1.2, 6 dB, and then tilt back up.
Right.
And it helps control TCP, which is total composite power.
Correct.
Because more frequency, more power creates more distortions.
Correct.
So you're always worried about distortions and noise when you're doing your designs. So by doing the step down function, we can control the total power. And still at those higher frequencies, we're going to run OFDM, which is more robust in the first place. So we might be able to, still do 4K QAM or 1K QAM. But we could do stuff like that with the biasing of the current of the hybrids too. So we could do the step down and save a little power. Or maybe you're like, you know what? I don't want to step it down that much. I'm going to step down my 254 to 1 gig 3 dB, and I'm going to step this one down 3 dB, or I might be able to finagle some things around.
So to your point, though, I think smart amplifiers are on sort of this 5-year plan that we're talking about. They're on that roadmap because it gives cable operators the ability, and AI, artificial intelligence, does come into part of it to play with this, because we can remotely, as you mentioned, once they're set up, cable operators can have systems that can continuously monitor smart amplifiers. As changes in the plan come, say an impairment, we can add a little bit more gain to these amplifiers to compensate temporarily for that impairment while we go out and fix the impairment. So it gives us a little bit more resiliency in our cable plan. A lot of cool features with it. Also, it takes away that the possibility that a technician could accidentally put in an incorrect pad or equalizer in the amplifier, because we have that ability to monitor the output of the amplifier while we know what padding is in that amplifier and equalization. So smart amps are pretty cool technology. I think we're going to see a lot more of it. There's multiple vendors that are making it, and that technology, again, to your point, there's a lot of training that has to go into explaining to a technician how to set up and balance and sweep and balance amplifiers. A lot of that can now be done automatically through processes, and then long term, there's a vision to have like AI just continuously monitoring that and then reconfiguring those smart amplifiers. So cool technology in that.
So that was the pads and EQs, right? So we're not carrying around all these accessories. Because it's electronic, you could have the fidelity of 0.1 dB instead of 1 dB increments, right?
Yes.
I mean,
a lot more accuracy.
You could accurately put it where you want it. To turn this back around on the upstream AGC idea, because we have a downstream automatic level control, automatic gain control that's monitoring certain downstream frequencies, you can extrapolate how much change happened on that downstream frequency and extrapolate it down to the upstream and make a circuit change on the upstream. So you could say, oh, I changed by 3 dB at 500 megahertz. So according to my math, that's going to be about 1 dB in loss at 200 megahertz. So I can change that upstream pad and EQ. In this case, it might be just a pad. You understand what I'm saying?
Absolutely. No, that's where I think it's almost like we have an amplifier now. It can be, to some extent, self-healing.
Yes.
You lose some gain in the return, and now you could add some amount of gain of that back in. Again, that's not the fix. That's not the. It's just a temporary Band-Aid while we go find out where did that gain go in the return.
But this might have been because of temperature.
And well, in that case, yeah. If it's just temperature changes, we're easily compensate for that for ALC. So very cool. That was thank you, Armin, for the question on smart amps. That led us on a exciting discussion. And and herding John takes a village. So we appreciate everyone pulling him back in. So John, what else should operators be thinking about on the 5-year strategy to upgrade their
another
plant?
thing I saw that Technetics was getting into, and I think this is a real departure from the norm, because we've been doing quasi-square wave 60 hertz powering since the inception of time.
Yes.
Since 1948, probably, right? We probably started with 30-volt power supplies in a coffee can. And then we went to 60-volt power supplies. That really put out about 63 volts. You need a true RMS meter to really measure a quasi-square wave voltage. You can't just use a regular voltometer. And then we went to 90 volts because power equals I times V. So if I have all these devices in the field that have constant wattage requirements, power equals I times V. If I make V go up, then I goes down.
The voltage drops after every amp.
So if I can increase my voltage, I have less current. If I have less current in my DC loop resistance coax cable, I have what they call less I squared R losses, which is that DC loop resistance and that voltage drop, right? So the less current I have through coax, the less voltage drop. The higher the voltage is, the less current drop. So it's almost like if you have low voltage, it's a runaway freight train.
Well, the current would go up really quick, and your amplifier would go into fold back, and now your whole plant drops offline.
Yeah, there's some protection there and all that, and even the mainline power supply has a fold back current. So, like, if it just had a short circuit, it wouldn't just say, "Hey, I need to provide
infinite
a lot more current, right? Infinite current." It's not just going to short itself out. So there's some circuitry there. There's some safeties there that we have that's built into a ferro-resonant power supply. We've been using this quasi-square wave. The reason we do a quasi-square wave is like taking a sine wave and cutting the tops off. Remember, we do an inversion where we take the negative part of that quasi-square wave and flip it upside down to make DC. Yep. And then in our amplifiers, we used to call it B+ for battery. And that's why we had that 24-volt DC test point, because that's what we're running most of our hybrids off of. Could be 24 volts, could have been 12, could have been 18. So the hybrids inside the amplifiers need DC voltage. So we have power packs. So those power packs do some of the conversion. Well, it turns out that we never did DC because we're worried about corrosion. And it turns out if you just cycle the power even at 1, 2, 3 hertz, meaning instead of
just
60
on,
cycles
off,
per second,
on, off.
yeah, you actually get rid of that corrosion consideration. And if you do that, you're closer to DC, and it turns out the power packs that are in amplifiers today will even work with this today. These power packs and amplifiers today don't really care about the frequency in that regard. So you could change your mainline power supply to a 1 hertz switching, you call it switching DC if you want, and it creates much more efficient powering. And Technetics did some studies, and they were showing a 30% reduction in total power. I'm like, that's pretty significant.
Yes.
It's like, and we're all worried about being green and doing more frequency and and all of our electronic power issues with too many electric cars out there. So yeah, there's all kinds of concerns with brownouts and all this other stuff. So, and we really are concerned with powering, not just saving money, but powering. This might have some legs to it. So it's going to be interesting to see if some people try this out. I'm interested to see it myself too. Like someone just to upgrade one part of their plant. Let's check it out.
It's going to be very interesting. And Charlie asked, does increased voltage increase potential for galvanic corrosion? I don't believe there's any association with the increased voltage. The reason that our power supplies, at least in the United States, stop at 88.5 volts is because at 90 volts, you need to be a licensed electrician to work on the cable plant. So by limiting it to 88.5 volts, you don't need to be a licensed electrician. And that's why our power supplies stop at that voltage.
If we didn't have that, we'd probably think about going to 220, right?
Yeah, exactly. I think we'd be able to go much further in our spans at lower current. E. Brown says, AI fixing or fine-tuning cable infrastructure and plant management is great. Just making it happen already, cable companies. It's slower than molasses. Frustrating as a consumer. Great comment. I love it. And Grab a Sandwich says, AI must be coming already. Layoffs all over the place at the MSO I'm a contractor for. Even slow enough that they're giving us next week off, potentially 2 to 3 weeks. Yay. Wow. Sorry to hear that, Grab a Sandwich. Hope you make some lemonade out of it and enjoy a vacation for a little while, and hope it comes back up for you.
Yeah, it's when you're a publicly traded company, sometimes you can read between the lines, and they'll say one thing, but they might be doing something slightly different, right? Yep. Like, even if I say I'm going to FDX, full duplex, am I really doing full duplex, or is it just full duplex at the node itself? Right. But it's really still simplex or half duplex. Because the modems will never be full duplex. You can't transmit and receive at the same frequency at that single house.
Right.
Now, I might have enough isolation between my house and, say, Brady's house. They were in the same neighborhood, but different legs of a node. His upstream could transmit while my downstream is coming to me at the same frequency, same instant of time, because we have enough separation and enough isolation between ourselves. So, yeah, there's some nuances there, right? So I think what is implied and what is actually deployed is different everywhere, and part of it is looking good to the market and make sure that everyone's happy. So it's like, yeah, we're going to jump on this bandwagon, and it's like, is it really happening? Altice, I used to support Cablevision in New York, and Altice took them over out of New York, and they got rid of. They said they were going to fiber everywhere. Then a couple months later, or a half year later, I think they changed their tune. Because, like we talked about, it's expensive.
Very expensive. So, John, we are about out of time. Anything coming up that you want to plug before we wrap it up?
I'm not going to Germany. I think you are, right?
I will be in Anga coming up very shortly. Not next week, but the following week. So if you're at Anga, please do stop by the OpenVault booth. I will also be speaking, and I will be talking about how AI can help plant network maintenance and proactive network maintenance. So it'll be a good opportunity there to catch up if you're in Germany.
Yeah, I won't be going, but I'm sure I'll be at the expo it's in Atlanta again, right?
Expo is going to be in Atlanta this year. Yes.
Yeah. In September.
Yeah, in September.
I think it's October or September.
We have more episodes between now and then. So, yes. All right, John. Thank you so much for sharing your expertise. I think that's a conversation between Tom's and Grab a Sandwich. We'll let that go. Thanks so much for everyone in the chat room. It was a great chat. If you missed out on the live episode, have any questions, please do drop them in the YouTube section below in the comments section. We'll be sure to get back to you. Otherwise, fantastic show. Thanks, everyone. So long. We will be back in June for another show of Get Your Tech On. So long. Take care.
And thanks for the feedback from the other guys, too, online.
Yes. Thank you, everyone.